Alright, so we have some new topics we're going to get into, but last time we went a bit over and we still didn't manage to finish everything. So we're going to finish first off our discussion of the semi-direct product. And as I said, this is a continuation. And continuation does not start with C. With O. It does start with C. Alright, so first off, we're going to look at a consequence of what we showed before. So we're going to have G be a semi-direct product of A by B with all of the maps you would expect, and this is going to be an essential. So essentially it's going to be a semi-direct product. And as you can tell probably by how I drew this, we're going to be defining another semi-direct product. I'll move the map back, of course. I think we'll write it with an inverse, probably would be more clear. Not exactly formal, but you know what I'm getting at there. We have a second semi-direct product. And we have a map. I drew this upside down, so I'm just going to flip this arrow from how you would expect it. It's going to be F. Alrighty. So what actually is happening here is we let phi be the map from B into the derivational algebra of A, and we let this new algebra G0 be the semi-direct product of B by A, might be of A by B, I might have mixed that up, but anyways. Nope, yeah, that is right. And we're going to define it through this phi. So essentially we have an indirect, we have an inessential extension of B by A. From that we can create a map from B to the derivations of A, and from that map we can then create a semi-direct product. And we just want to make sure that everything lines up here, that this semi-direct product we're creating is the same as our original. And keep in mind, because this is an essential, the kernel of the top extension is supplementary to the map V, map new, which is we're showing the inverse here. And then we have that the map from A comma B, which is G, now this is from GO to lambda of A plus nu of B is, and so this is actually what F is going to be in this map, and this is an isomorphism. . And of course this whole diagram is going to commute, So the two different extensions, the extension we generated essentially is equivalent to our original extension. Alright, let's take a look at some examples of semi-direct products. So we're going to, of course, let G, in this case, be a Lie algebra over F. And take some derivation D inside the algebra of derivations of G. And this is kind of a new construction here. We're going to let H be F as a commutative Lie algebra. And so, if you recall, what we need to turn, so a field can kind of be a vector space of itself, where the sum is the sum of the field and the scalar product is just the product of the field. And we have, of course, an analogous construction for rings and modules. And then to turn that into a Lie algebra, as we saw way earlier on, you always have the Lie bracket, which just sends everything to 0, which, if not in field of chart 2, is by antisymmetry the only way the bracket can be commutative. And so that's what we're doing here. H is a commutative Lie algebra, the set is just F, the addition is just the addition of F, scalar multiplication is just the multiplication in F, and the bracket is just 0. Okay, and so we're going to define a mapping from lambda to lambda d for lambda in F. And this is a homomorphism from H, this algebra H we've created, and this mapping onto the derivations of G. Now we're going to let this element XO be, alright, no, hang on, first, with this map, we're going to call it phi. And this gives us a semi-direct product of H by G. Going to call this T. Now we're going to let XO be 0, 1 inside T. Then for all X and G, we get that D of X is the same thing as the bracket of XO with X. Because keep in mind, XO under the map phi is just going to give us 1 times D, which is just going to be D. So this essentially, yeah, it should be pretty clear what's going on here. I guess we'll call this example A. Now I get example B. We're going to let G be Lie algebra over F as before. We're going to let M be an F module. So I guess this is a ring. I guess that's why they're using K. Whoops. Anyways. And rho from G to the general linear Lie algebra, which is just the endomorphism algebra, a homomorphism. Once again, we extend M to be a commutative Lie algebra. Then we just have that the derivations of M is the same thing as the general linear Lie algebra of M. Thus, we can let H be the semi-direct product of G by M through our map rho from above. Alright, so now to be more particular with this, going to let G be equal to GLM, and thus this map rho is just going to be mapping from GLM to itself. And so there's a very obvious map to pick for that. In this case, H is denoted as the, I believe that is the affine algebra, it's going to be called, of M. And we can define the n-dimensional version of this for just M being our ring to the power of n. And so we have our bracket as the bracket of M from our module and U from the general linear Lie algebra of our module, with some other bracket of m prime and u prime. Now keep in mind the formula for the Lie bracket is going to be the bracket of m by m prime, but since m is a Lie algebra through the commutative bracket, that's just going to be 0, that's going to cancel out. And so we're left of u of m prime minus u prime of m with the standard bracket of derivations of the general linear Lie group. I guess I should be using round brackets for the outside here, otherwise this is going to look real confusing. And there we go. Yeah, okay. And it says here explicitly, when M is a finite dimensional vector space over the real numbers, AF of M is identified with the Lie algebra of the affine group of M. And I'm believing they're talking about the correspondence I alluded to earlier, where this is kind of the tangent space of the affine group at the identity element. Now we have a little further discussion here about the semi-direct product. Let T be a Lie algebra. I'm going to go over K because I guess these are rings, so F is going to be misleading. Oh, this is more discussion of the affine Lie algebra. So we have a linear map theta of T into the affine group of M can be written as theta of T is equal to one of the fun things about reading these books is trying to interpret the typos that no one bothered fixing. I believe that's eta of x, and this is eta of x. I gotta learn what that element on the left is. Where these two functions we have here, from T to M, and of course the other one you can see obviously is going to be from the general linear, from T to the general linear of M. These are both going to be linear, obviously. And so the question is, what constraints can we have on this map based on the fact that theta is a homomorphism? So write it down. Well, what does it mean for theta to be a homomorphism? I guess it's not necessarily homomorphism, that is an assumption. But in the case theta is a homomorphism, well, we know it has to interact with the Lie bracket in a very specific way. So we have to get the bracket of theta of x and theta of y. And we can write this using the above formulation. What the hell does that mean? One second. Alright, well, I'm just going to assume that the recording is still fine, and if it's not, I'm just going to cry a bunch later or something, I don't know. We have from the above formulation, this is going to look like the first component is going to be this first one of the bracket, and of course the second one is going to be the second. And this is going to, of course, split into across the brackets. And then we can, because of the way the semi-direct product works, we can actually, we have the formula above here, right? So if we just plug that in, we get that this has to be look something like this, because the elements on the right are going to be in the general linear group, and the elements on the left are going to be in the module that we're looking at. And then this element on the right is just going to be the bracket. Okay. You can see from this is a homomorphism if and only if the term on the right into the general linear group space, not group, the algebra is itself a homomorphism, and that we have the element on the left interacts with the Lie bracket as such, which is just going to be the first term, right? And keep in mind, once again, these periods are evaluation, because the image of the elements in the group in the algebra under the bar on the right is in the general linear algebra. Alright, so these are our constraints on the two halves of theta. Oh, so in this case, I guess this algebra that T is over is going to be the same one, so we're going to have to switch back to F, because everything needs to line up. So now, let N be the F module. I'm regretting not using K. Of M cross with F. We're going to let T again here be the subalgebra of the general linear Lie algebra of N consisting of the elements W in GLN such that they satisfy the condition that the image of n under them is inside of M. So essentially, the output of these W always has a 0 on the module side. So then I guess we're going for all W and T for every such element. We're going to let the image of W under eta be a new element inside GL of M. B, and this is just going to be the restriction of W as a function to M. And we're going to let our other side be equal to just evaluating W on 0, 1. Since W has to be linear, essentially we can extract how it works across F from this one element. And keep in mind this is still going to end up inside of M. Thus, for W1 and W2 inside of T, this function W1 and W2, the bracket W1, W2 is going to be equal to W1 of this of W2 minus W2 of this of W1, which is just going to be more clear, that's a bracket. Eta of W1 eta, sorry, get rid of that period because those are notationally important. Evaluated on this of W2 minus W2 evaluated on that thing of W1. Hence, the mapping, based on the conditions we had before, of W to what you would expect is a homomorphism. We're going to call this theta. T into the affine algebra of M. So we have as theta is bijective, we can just set phi to be the inverse of theta. We'll see here if we have this mu inside the affine algebra of M, then theta of mu is equal to W such that W of some m prime and lambda is equal to m plus lambda m 0. So these halves have to work in the way you would expect. There's a note here that the affine algebra of M is often identified with the subalgebra T of the general linear Lie algebra of N under this theta. Alright, on to our last topic before we start getting into the heavy algebras here, which is going to be change of base ring. And hopefully you can end today by finishing off this topic. It doesn't look like it'll be too long. So we're going to let KO be a commutative ring with a unit element, and rho is going to be a homomorphism from KO into some K with so I'm guessing it's going to be a ring, at least it's got to be commutative, right? With 1 of KO being sent to 1 of K. We're going to let G be a Lie algebra over K. We can define a Lie algebra G prime over KO by G and our homomorphism rho. Now how this works, addition and the Lie bracket of G are internal, and so we can transfer those over without issue. And Lie bracket are the same for both. The only change here is scalar multiplication. How scalar multiplication works is gonna let, okay, so we have our KO to K be our function rows above. Now we have a function from K to G defined as I'm going to go kx for x in K. So essentially what's happening here is the way we're looking at scalar multiplication, we're picking some element in. So the way scalar multiplication works is it's by an element of the ring, an element of the module. So essentially we're picking our element of the module first, and then we're picking our element of the ring and sending that to their standard scalar multiplication. And our new scalar multiplication is just the composition of these two functions. So for k0 inside k0, the way you scalar multiply an element of g prime in this case would be equal to the scalar multiple of whatever the image of ko under rho is, and with the standard scalar multiplication formula. And keep in mind, this is just like, I guess we should have like g prime, and this is going to be the natural map. And so this is going to be our product. Kind of a messy diagram, but I hope you understand what I'm trying to get at here. It says the subalgebras, or alternatively the ideals, of G are subalgebras, or alternatively ideals, of G prime. A and B are submodules of G, then their bracket, A bracket B, bracket of sets, is the same on G and G prime. As we have that okay, so A, B, is going to be the set of sums of elements xi, yi, for x, y, for x in A and y in B. And our bracket, as we said before, is just going to be inherited directly, and so that's not going to change, and so any of the constructions that we see going forward with the bracket will be the same over the change of base. Also, the centralizer of a subset, keep in mind, it is the same in both. Keep in mind that the centralizer of H in G is x in G, such that the bracket of x with all of H is just the element 0. And as this is a bracket-based construction only, as this doesn't use scalar multiplication at all, this is going to be the same on G prime. Alright, so new idea here. Let K1 be a commutative ring with unit and sigma a homomorphism. Sigma is going to be a homomorphism as before from K to K1 this time. So it's on the other side. And then once again, sigma maps the unit element of one to the other. Let G be a Lie algebra. That is a G, not an A. Over K. It says let GK1, in this case, notation, be the algebra over K1 derived from G by extending the base ring. And to give a reference, which I'm going to have to look into to get the exact details of this, I might start off the next video with that. But then this GK1 is a Lie algebra. Once again, if A is a subalgebra or ideal, of G, then its canonical image, AK1, is a subalgebra or ideal of G extended to K1. If A and B are submodules of G, then the image of their bracket is the bracket of their images. If F is a field with an extension field F1, and the canonical injection we're going to write as sigma, then if we have all the same details as you would expect. The bracket of the extensions is the extension of the brackets, and so on. If M is a finite dimensional vector space over F, of course, then its extension by F1 as above is a finite dimensional vector space over F1 and the associative algebra, which is a topic I'm not actually directly familiar with. One is canonically identified with the extension of the image, as you'd expect. So the Lie algebra of GL also transfers over. So I don't know exactly how they're doing this transfer, but I've seen one example of case which I want to give as a reminder anyways. And that is complexification. This is one example of changing a base through the tensor product. It all generalizes pretty naturally in the way you would expect, but I'm just going to give a brief overview as you would expect. So let V be a real vector space. The complexification of V is defined, and they write it here as the exponent, it looks like. And this is the real tensor product. This would be easier if I draw the circle first, although it didn't turn out much better. Of V by C. And so this is itself is just a real vector space still, despite what it looks like. Because keep in mind that what the real tensor product means is that it's going to be that the scalar multiplication you get with the tensor product currently is only defined over the real numbers. And so we have to define complex multiplication. Complex scalar multiplication. Keep in mind this isn't algebra, so we don't have an internal product. As this is going to be, so our element in VC is going to look like some vector V, tensor, some complex number beta, and the complex product with a complex number alpha. We're just going to set it. Keep in mind that the tensor product is bilinear. In fact, it can be defined as most general bilinear product function. And so real scalars are going to factor into either side. There's no obvious way to factor alpha into the left side here because it is a real vector space. But we can very easily just factor it into the right side. And this is going to give us an element inside V of C, which we can then compare with other elements of V of C as you typically would with a tensor product. and we're extending these scalars. An easier way to think of what elements in this space look like. So if alpha is equal to x plus yi in C, where x and y are of course real, we can write that the tensor product of v with alpha is just the tensor product of v with x. It's going to be, I guess we should write it like x times the tensor product of v with 1 plus y times the tensor product of v with I. And keep in mind that we're looking at the completion of the space, like the space as a full, so in general, so this first case is for v in our original vector space, and v in our complexification in general is going to look like v equals v r tensor 1 plus vi tensor I, for VR and VI being two real vectors. And in this case, our product is just what you would expect, a plus ib, so VR plus VR plus IVI, which is how we're going to write this term here. And this is going to look like what you would expect. AVR minus B VI. This can be a real component, and our imaginary component is going to be, of course, BVR plus AVI. And so our complexification is going to just look like V plus this notated as IV. And of course, we remember that from the dimension of the tensor product being the product of the dimensions of its constituents, the dimension of this thing is going to be twice the dimension of our original space, which is going to be the same thing as the complex dimension of our new space being the dimension of our original. And hopefully this just gives you a bit of insight into how this thing works. This isn't actually a direct part of Lie theory, but this is kind of what made change of base click for me, and so I thought I would just include this as like an example in a non-Lie setting. But you know, it's a toy example. Hopefully it should help, and we will call it there for today.